What's going on, everybody? I hope you enjoyed the last video. I sure had a good time. So we're going to be moving on to Behemoth 1 today. By the way, I forgot to mention this last video, but if you're interested in this challenge, you should definitely attempt to do it yourself first before watching my video, because I'm basically going to spoil it for you. And they also technically tell me not to give away the answers like this, but I don't think it's a big deal. I'm having fun. When I finish these, I like to look at other people's solutions to see what they did, so hopefully they don't sue me. We'll see what happens. Alright, so last time we did level 0, moving on to level 1 today. Hopefully this is not too hard. I don't totally embarrass myself. Alright, so now we got Behemoth 1. Let's see what's going on here. And yeah, basically all these are the same. You have set UID programs, and you're basically trying to trick the program to execute a shell for you with the user the next level above you. Alright, another password level. Authentication failure, sorry. Alright, let's take a look. I'm using obj dump again. This one. Alright. We got, looks like we just got a little guy today. It's got a main. Alright, we got looks like we got printf, get, and put. Yep, this one. Alright, we're getting into the real stuff now, I think. I think what we're gonna do is buffer overflow here. So those are kind of fun. Let me just check something real quick. I believe the get function is like one of the most unsafe functions you can use, because it, yeah, I remember reading that at one point. Yeah, so this function is really stupid. It just literally, you give it it just takes input from the user, but it doesn't check the length, so it's just gonna, you can just like, maybe it'd be better if I just demonstrate. So with 1, if I just go blah, like just give it way too much input, I actually caused a segmentation fault, most likely because I overwrote the return address from main, so it's trying to go to some bullshit. Here, actually, we can see. We can verify my theory. strace. Alright. So we get a segmentation fault at the address 6F, 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 6F. So that's these O's. These O's are 6F in under, like, at the machine level. So there was a valid return address here, but it got overwrote with these O's, and the gets function is so stupid that it doesn't know any better. So that being said, what we can do, instead of giving it a bogus return address, we can actually give it an address to some code that I'm going to inject into this program that is going to spawn a shell for me. So when I was doing Narnia last time, I apologize for that knocking behind me, by the way. So yeah, I did the Narnia challenge for Over the Wire previously, as I said, and I use this shell code to execute shells. This is like the actual machine code bytes. So like if you can get the process to execute these instructions, you're gonna get a shell. And as far as how I got this, I fortunately did not write it myself. Just went to this cool little thing called shellcode database, And you can see all sorts of different cool stuff that you can do here. Oh, not this one. All right, you know what? It's not important where I got it from. Someone smarter than me wrote this code. I just copied it from them and used it in the right spot. Doesn't matter. That's what hacking is all about. Taking from the knowledge of others. So now the question is, how do I inject this into the process? So one problem you're gonna run into is these are just like, most of these are not like this 31. I think this isn't like some button on my keyboard that I can press. It's like it's a non-readable character, so I have to kind of programmatically send it as input to the program. So one thing I like to do a lot is use Python. So for example, if I do this, so Python, this -c flag is just going to execute like Python commands on the fly for me, so I don't have to like write it into a file. Saves you a lot of time. So if I do, let's take the first byte there, 31, and I do that times 1,000, right? Oops, forgot. Print it, right? It's gonna go to standard out. Oh, you know what? I lied to you guys. That is a human readable character. That is the one. Let's pick one that's not human readable. C0. Okay. Yeah, I mean it's readable, but I can't type that on my keyboard, right? So I have to use Python to send like certain bytes into the process. So what I can do is now pipe it into this program, and it really doesn't know the difference whether you're sending stuff through your keyboard or sending it through another program. So if I trace this, you know what? I was gonna try to show you guys something, but I think trace only gets the first program in your pipe, not all of them. And honestly, I don't remember how to change that. So you're just gonna have to take my word for it. It segmentation faulted with these C0 characters. All right, so that's still gonna give it a seg fault. So what I need to do is figure out like at some point in this string that I'm passing in needs to be the 4-byte return address that the program expects in a certain spot, and it's going to jump to that code. So one thing that's really helpful for figuring out where that is going to be GDB, like we used last time. So we look at the main function, and we look at gets here. So I'm going to go right after gets, put a breakpoint there. We're going to run it, and we're going to... Okay. So now, let me try to explain to you guys how this stuff works. So if you look at the stack, I look at like the top 20 words, which if you remember is like a 4-byte, it's 4 bytes, and that's like a common unit that is used because this is a 32-bit program. So all of the memory addresses, the integers, all your pointers are going to be 4 bytes long. So that's why it's very useful to look at these in words. So top of our stack is at this address here, and you can see I just overwrote everything with these O's. And when you return from a function, so that's this instruction here, what it's going to do is So it's gonna look for the last address that it was at before it called into this function, and it's gonna jump back to that address. And that address is conveniently also stored on the stack. So if we look at, there's this other register called the EBP, the base pointer. So we got our stack pointer, we got our base pointer. And every function has a new one of these basically. Oops. So we can see that from the base to the stack, there's 72 bytes. So that's pretty much how much space the main function had to work with. Okay, and so every time you call a new function, the base pointer gets saved onto the stack, and then it kind of gets swapped with the stack pointer. Probably not explaining that very well. So basically what you need to know is here is going to be the function that called main's old stack pointer was here. It's C8, and then it jumped up to 680 here. And so before it jumped up, what it did is it pushed. Actually, let's restart this program. So I already overwrote what I'm trying to show you. So I'm gonna put it before I call gets. I'm gonna put another breakpoint, right? Okay, and then we're gonna restart the function, the program. So now we're gonna look at the stack before it copied in my input. Okay, so we got what is going to become this used to be this. And if we look at the base pointer, this is the old stack frame. So, okay, what we have here is, actually, what is going on here? I was expecting to see this guy, because this looks like the return address for the other the caller function. This is I'm pretty sure this is what we want to overwrite. I thought I would see it here. All right, guys, maybe I'm not as smart as I think I am. Let's just give this a whirl. So I'm gonna continue to the next breakpoint. We're gonna put in a bunch of A's here. All right, and then let's take a look again. Okay, that was too many. Looks like that was about 4, 8, 12 too many. All right, let's try this again. So the ESP here, and then we're gonna copy this. Continue. We're gonna paste this in. 1, 2, 3, 4, 5, 6, 7, 8. I'm gonna put different characters here so you can see what I'm talking about. E. Okay, so then we got A, and then here we got our. Oh, looks like I didn't count right. I'm off by 2 here. It should all be. So let's try it again. Well, doesn't matter. We can. Okay. This is very interesting. So I really thought that I've been looking at these a lot, and this number, this 0804, these are usually, this is the part of the memory where the code usually is, so that's why I thought this would be the return address, but it could be something else actually. So yeah, maybe I should go with my first instinct, which is that it would be at the base here. You know what? Yeah, it's this F7 guy. This is another part of the memory that has code, I'm pretty sure. So what we're gonna do is, let's try this again. So you know what? I'm actually gonna look something up really quick. GDB pipe input. Yeah. I don't want to use the file name. Try something here. Just because it's not ideal to have to manually type out the A's here, so what we're going to do is run. Yeah, alright, I think I can do this. So Python C A times 100. Okay. Yes. Oh, that's not gonna work. Oh, come on. There's gotta be an easier way to do this. Okay, whatever. Let's do this the hard way. Alright. I'm gonna try something else now. I know that there's 72 bytes on the stack, so I think what I can do is I'm gonna use hold on. Strace follow pipe. Strace F. Okay, alright, that works. Yeah, alright, let's try this. So I'm gonna do strace. I'm gonna do Python print A times 76. A times 72 plus this, and then pipe. Alright, so what I need to shell. Okay, let's try. Let's see what that looks like. Okay, looks like I'm just trying to see if it actually followed both of them. I think it should have, but I think I didn't write far enough to overwrite the memory address here. So 76. Just gonna increase by 4 until we hit a seg fault, and that should mean that I hit the return address. I'm not sure what's going on here. Oh. Yeah, I'm piping the shell itself into Behemoth, not the. Alright, let's go. Yeah. Still no seg fault. Okay. I bet if I take out the wrapping. Oh. Right. No? This gotta be a better way. Follow for it calls. Oh. That's a great idea. Alright, yeah. Okay. Sorry it's taking so long, guys. Okay. So what I want to do here is, so this should give us a seg fault. Okay. So if we hit the seg fault, 72. All right, and then we can just put strace in front of here. And okay, so you can see I put in, I tried to put in dead beef, but I actually messed that up. And then it looks like I was off by one character here because one of these the 41 here got fit in at the end, so let's try 73. Oh, okay. Wrong direction. Let's try 71. Alright, there we go. So we hit. Now I've replaced the return address with this hexadecimal number, which looks like the word dead beef. And now I know that I have 71 characters before, and then I have my return address, and then here I'm gonna put my shell code. Just gonna copy this from here. Oops. And then actually yeah, okay. So I'm gonna do, I guess I have to, I'm gonna save this to a file. Okay, so when you're on these servers, you can't actually make files in your own home directory. Probably because everyone else could see what you're doing then. So what they have is they let you make like your own temp directory. So what I can do is do that. And oops. Okay, and I can, awesome. So I can actually make files in here all I want, which is really useful. So now I'm gonna do is I'm gonna save this input. Okay, so I got my A's, I got my return address, and then I got my shell code. You can kind of tell what's going on because it's got the bin/shell, which is like the executable file that they're going to be running, and then there's a bunch of gibberish, which is just the ASCII representation of these bytes here. So now I'm going to go to GDB. Take a look so we can figure out what the return address needs to be after gets here. So put a breakpoint right here. I'm gonna run input.txt. And we're gonna look at the stack. Alright, there's our dead beef guy right here, right at the end. And then we wanna, let's get 4 more down here. And then looks like this is our shellcode, I think. Should be, looks like it. 80. FFFFD6 80. That's where we want to go. So right now, dead beef seg faults. That's not a real it is a real address, but you probably nothing useful there. And so we're gonna update our input file. I'm not gonna do it. I'm just gonna do it like this. We're gonna place dead beef here with. Oh yeah. This is kind of confusing, but when you have a word, the bytes that make up the word are actually stored like in little. It's called little endian. So this byte is like stored first, and then this one, and then this one, and then this one. So like the smallest byte goes first, if that makes sense. It's kind of weird to me at first, but the more I kind of thought about it, I guess it does kind of make sense. So let's do that. Updated our file. We're gonna run it, and oh, look at that. So this is good news, guys. Process is executing a new program /bin/dash. That's our shell. So GDB actually executed a shell for us. All right. So hopefully we can do the same thing outside of GDB. Sometimes it doesn't work out, but be hopeful. Ah, dude, segmentation. All right. I was afraid this would happen. FBADZ. I have no idea why it's trying to. Alright, well, one way we can mitigate this is with something called a NOP sled. Or a no-op sled. So, there's this cool machine instruction with the byte 90, and it literally just does nothing, but you can use it to kind of pad your shellcode. So, if you don't know the exact return address that it's going to be at, I'm just going to put like 200 of these guys in here, and then this way I have like kind of a lenience of where this needs to land. It just needs to land in one of these 200 byte 90s, and then it's just going to kind of slide through them doing nothing until it hits my shellcode. So hopefully that is going to work. Let's see. Okay. I got a segmentation fault. I'm just going to kind of play with this number a little bit, just to kind of see what's going on. That's... okay, you know what? I don't need to mess with this text file anymore. I'm not in GDB, so I'm gonna just pipe directly into illegal instruction. What the fuck? Alright. Might be going the wrong way. Segmentation fault. This is not working out so well, huh? Let's S-trace it, just see what's going on. Okay, so it's got an illegal instruction at FFD632, and alright, that's kind of what I'm passing in here. kind of tricky to figure out. Alright, what was the first address I tried? D680. Let's kind of try to stay around there. Let's trace it. FB8D0. Alright. 70. FFD69E is an illegal instruction. Okay. And oh boy, guys, this isn't working out so well. 90. Oh. Just worked. Oh. Wait. My knob sled disappeared. It's like not seg faulting, and it's not giving me a shell either. And I bet, pretty sure I still have the right address. Yeah. So when I bump the A up, it goes into this thing, but it just, so it's, that is weird. It's executing something, but it's not this shellcode. That is weird, man. That's okay. Oh boy. Okay, I'm gonna try something else. So, hey guys, I'm back. Sorry, I had to do a little bit of research, but I think figured it out. So we have the right address. The problem is, so we do this. We don't get a segmentation fault, and we also don't get a shell. And if we S-trace it, then we can kind of see why that is. So I'm going to pass this -F flag. So that means if it executes a child process, for example, the shell, then we're going to see what's going on there too. So here we can see it is executing the shell, but for some reason we can't actually give it any input, which is a problem. The reason is because it's still attached to the standard input from Python here. So we need a way for it to also take input from us after the fact. But that's fine. So what we can do now is this cool little trick that I just learned about. I'm not ashamed to admit that. So what we're gonna do is we're gonna pipe this into the input file. Okay, and if we, just to verify that it works, we're gonna cat this into Behemoth/Behemoth1, and then, okay, let's look for the, yep, all right, it's executing the shell. And what we want to do is basically run this guy in like a, what's called a subshell. And so we do like that. And then what we have here is, well, let's get rid of the S-trace. Boom, we have our shell, Behemoth 2. Took a little longer than I was hoping, but we got it. And so the way that worked, let's grab the password real quick, and then I'll show you how that worked before we move on to the next one. I always mix up echo and cat. There we go. And then I can exit out of that. So like, the reason that worked is the first cat, put this in, and then like by wrapping this in parentheses, we're getting the input from everything here. So this finishes after it reads the file, and then this cat executes, and when you just run cat by itself, well, it's basically just takes your input and copies it back. So yep, that's how it works. All right, and now we can hopefully do number 2. All right, we're in. All right, I will see you guys next time. Thanks for tuning in.